Welcome back to our course on linear feedback control. My name is Kai. We'll be starting to introduce state models for dynamic systems. In this video, we'll first introduce two basic concepts, block diagrams and linearity. Let's start with block diagrams. A block diagram is a graphical representation of a function. Consider function f from set x, we call domain, to set y, we call codomain. We'll represent this function using a block diagram as displayed. We draw a box, label it with the function name f, and draw an arrow entering the box from the left, labeled x, from the domain set big X, and an arrow exiting from the box to the right, labeled y, from the codomain set big Y. Now for a simple function f from real numbers to real numbers, we can visualize it as a graph in the xy plane. However, not every curve in this plane represents a function. Remember that a function must be either one-to-one or many-to-one. Namely, each input can map to only one output. So if you draw a vertical line, and if the line intersects the curve more than once, then that curve doesn't represent a function. Here, the left curve represents a function, while the right doesn't. Next, let's look at an RC circuit. We have an input voltage U on the left, a resistor R, and a capacitor C. The output voltage Y is measured across the capacitor. The circuit equation is RC Y dot. Here y dot is the time derivative, the first derivative of y. So RC y dot is the voltage across the resistor. So this RC y dot plus y should be equal to U, so the balance of the voltage across the circuit. We can represent this circuit as a system using a block diagram with input U and output Y. The block itself represents the circuit's dynamics. Thus, a block diagram is a graphical representation of a system that transforms input signals to output signals. Here's another example from mechanics. Consider a cart of mass m that can move horizontally along a line. Let y denote its position. According to Newton's second law, F equals ma, the force F is the input force U applied to the cart, and acceleration a is the second derivative of position, namely y double dot. So this is the second derivative of the position y. So we have u equals m y double dot. Again, we can represent this mechanical system with a block diagram with input u and output y. Block diagrams also include summing junctions. These are represented by circles where multiple signals combine. The summing junction on the left means y equals u plus v. Here, addition in summing junctions is the default, so the plus sign is often omitted. The summing junction on the right means y equals u minus v. So for subtraction, the minus sign has to be written. These junctions allow us to represent how signals are dependent on other signals. Systems are not limited to single input and single output. We can have multiple inputs mapping to a single output, single input mapping to multiple outputs, and multiple inputs mapping to multiple outputs. Let's now summarize the key components of block diagram that we have talked about so far. A block diagram consists of three things: arrows, boxes, and summing junctions. Arrows represent signals. There are two types. Arrows without sources represent independent signals, while other arrows represent dependent signals. Boxes represent systems or system components. These are mathematical functions mapping signals to signals. Finally, summing junctions combine multiple signals through additions or subtraction. These three elements can be combined in various ways to represent complex systems, like the displayed feedback configuration. Now let's switch gear to our second topic, linearity. This is a fundamental concept from linear algebra. Consider a function f from x to y, where x and y are vector spaces over real numbers. F is called a linear function or linear transformation if for all vectors x1, x2 and all real numbers a1, a2, this equation holds. In other words, the function preserves the linear combination. Now let's consider a function f from Rn to Rm. Here is a basic fact. This function is linear if and only if fx can be written as a times x, where a is an m row and n column matrix. Let's prove it. We have two directions to prove, if and only if. First, for the if direction, let's suppose f equals ax for some matrix A. What we want to prove is that f is linear. Namely, and this is by definition, that for all vectors x1, x2 and all real numbers a1, a2, this equation should hold. So let's pick arbitrary vectors x1, x2 and arbitrary real numbers a1, a2. Then f of a1, x1 plus a2, x2 is equal to, here let's use the assumption that fx is equal to ax. Here the x is a linear combination of x1 and x2. So we apply a, so it equals a times the linear combination. So a times bracket a1, x1 plus a2, x2 bracket. Now, we can time this out based on basic matrix algebra, equals a1a times x1 plus a2 times a x2. Here let's use assumption one more time. Namely, we apply to ax1 from right to the left. Ax1 should be equal to f of x1. Ax2 should be equal to f of x2. So we have a1 times fx1 plus a2 times f of x2. So we used the assumption again, and here's what we want. So this is really the definition that we want to prove, and we have shown that f is linear based on the definition. So this concludes the if direction. Next, for the only if direction, so let's suppose the other way around. Suppose that the f is linear. What we want to show is that fx can be written in the form of a times x for some matrix A. Now let's consider the standard basis of Rn, E1 to En, where Ei is a vector where 1 is at the position of I and 0 elsewhere. Any vector x in Rn can be written as a linear combination of this basis and is equal to the column vector a1 to an. Now let's define this matrix A like this, where each column is f applied to a basis vector. Then fx is equal to f of a1, e1 plus all the way to an, en, namely the linear combination of the basis vectors. Now let's apply the assumption that this function f is linear. So we get a1 times fe1 plus all the way to an times fen. This can now be written as this dot product, where the matrix on the left is our defined A, and the vector on the right is x. So we get fx is equal to ax. This concludes the only if direction, and therefore our whole proof is complete. So we have established this basic fact that a necessary and sufficient condition for a function f to be linear is that it can be written in the form of a matrix times a vector. We will also need the extension of this fact to multiple arguments, namely for a function f from Rn cross Rl, this is Cartesian product of Rn and Rl, to Rm with two vector arguments. In this case, this f is linear if and only if there are two matrices instead of one, two matrices A and B, such that f of x comma y is equal to ax plus by. This fact can be proved similarly. Okay, so that's all the content for this video. Thank you for watching and hope to see you in the next video.